Larry and hot gaiters.
Thank you. Okay, so as advertised yesterday, in this lecture, as well as the next, remaining 3 lectures I'm going to be giving, I'm really going to be exploring the extent to which one can, first of all, do calculations of interesting physical quantities in strongly coupled thermal n=4 super-Yang-Mills theory. And so that will be sort of an exploration of using ADS-CFT duality, and to the largest extent possible, I really want to go through some examples and details and not just quote and tell you, oh, one can find this result and it can be shown that, because one of the messages is really to just show how remarkably simple some of the actual applications are. But all of this is motivated by the hope that properties of hot n=4 plasma are sufficiently similar to properties of hot QCD plasma that these results are actually useful. And so that's a question I'm going to come back to, for some comparisons addressing that, hopefully at the end of this lecture. Okay, but to start, you all know something about QCD. You've all heard at least a little something about maximally supersymmetric or n=4 super-Yang-Mills theory. If we were talking about zero temperature physics and somebody stood up here and said, I want to use n=4 super-Yang-Mills because it's going to teach me about zero temperature QCD physics, for most purposes, this would be a pretty foolish proposition. And I actually want to emphasize just how foolish. I mean, what are the most important aspects of QCD? Physical aspects more than formal aspects. Surely one of the most important physical things is the mere statement that it has particles. Particles exist, right? Honest to God, stable excitations, infinite lifetimes, little lumps that carry energy and momentum, everything we normally mean by particles. All right? n=4 super-Yang-Mills theory is a conformal theory. That really, honest to God, means it does not have particles. Right? You know too much. And in particular, the moment I turn on a temperature, it destabilizes that whole moduli space except for the origin. So here I really mean at the origin of moduli space. Right, so in particular, there's really an S matrix, a unitary S matrix that describes scattering in QCD. There is no S matrix in n=4 super-Yang-Mills at the origin of its moduli space. And of course, QCD is asymptotically free with non-trivial renormalization group flow. n=4 is conformal with no renormalization group flow. All right, and an immediate consequence of that, that's really just saying the same thing in other words, is QCD has a fundamental scale, usually called lambda QCD, and there's no such fundamental scale over here. All right, I put that up there merely to contrast with a similar sort of very quick qualitative comparison at non-zero temperature. And for QCD, when I say non-zero, I really mean sufficiently large that it's in a deconfined phase. So what are the most important qualitative properties? Well, surely in this regime, I just start with the statement that we really have a system which is behaving, which is some sort of non-abelian deconfined plasma. As I talked about yesterday, that is something you can truly justify in QCD. And everything I said about the asymptotically high temperature regime of QCD, one can really repeat the whole analysis over here in n=4. It really didn't depend on any of the details. So the fermions here and the adjoint representation and the fundamental over there, it doesn't affect any of that discussion about fermions being anti-periodic and essentially decoupling at high temperature. I talked a little bit yesterday about Debye screening, and I'll say some more about it today. And again, Debye screening is a property that's really generic. It says you have some sort of system in which you have charges that are mobile and they're free to move around. So you stick in a test charge, and of course the mobile charges are going to rearrange their distribution and try and screen that test charge. It's true here, it's true over there. If you measure spatial correlation lengths, because of the simple long-distance effective theory in the asymptotically high temperature regime over here for QCD, where we just ended up with a three-dimensional description that was pure Yang-Mills theory that develops a finite correlation length. That's a property here. And once again, exactly the same arguments would tell you it's true over here. Something I didn't talk about yesterday, and I'll hopefully get back to later this week, is if we now think about displacements from equilibrium, slight non-equilibrium properties. In other words, take a box of this hot plasma, shake it a little bit. How does it respond? All right, I will argue, or at least I will assert, that the appropriate description for hot QCD is simply hydrodynamics of the simplest possible neutral fluid. In other words, hydrodynamics where the only variables that are relevant are simply a local fluid velocity. That description applies here, and exactly the same arguments will apply to n=4. So the point here, I think, is obvious, that while there are enormous qualitative differences between QCD and n=4 super Yang-Mills at 0 temperature, all the qualitative properties are exactly the same in the deconfined plasma phase. And therefore, it becomes an interesting question to say, how much quantitative similarity is there? And that's, well, motivating all the efforts to really now study in some detail, quantitatively, properties of hot n=4. Okay. I'll skip that. So I just want to put up here for reference the dictionary in terms of basic parameters. The conventionally defined Yang-Mills coupling is directly related to the conventionally defined string coupling this way, the 't Hooft coupling lambda in the simplest gravitational duality, as I think has been mentioned a couple of times here, is related to the fourth power of the ratio of the curvature scale that I'm going to call capital L divided by the string scale that I'm going to call little l. Okay, so at zero temperature, there is strong arguments, some of which you've heard, some more of which you're going to hear later this week, that this theory really is exactly described by type 2b string theory on ADS5 cross S5. And I'm certainly just going to take that as a given. The first thing I have to talk about is how do we turn on a temperature? So if I now want to consider thermal properties over here, it has to make some change in this description on the other side. And how do you do that? Okay, well, what do? We have already seen that any question that involves equilibrium properties, I can repackage in terms of a Euclidean functional integral which is a functional integral involving fields which are taking values on R3 cross S1. I guess this is a good time to comment that everything I talk about, I'm going to be thinking about this field theory formulated on R3. You don't have to do that. In particular, there's a version of this duality that's understood where you can instead introduce finite spatial volume, not by doing a compactification on a torus, that turns out to be hard, but by compactifying on a 3-sphere. But just to narrow the scope of what I'm going to talk about, I'm going to ignore all that finite volume discussion and only work in infinite spatial volume from the outset. Okay, well, at zero temperature, defining the theory on R4 is related to a gravitational dual defined on ADS5 cross S5, and ADS5 has a boundary which is R4. And you really, in some heuristic sense, can think of the field theory as living on the boundary of ADS space. And that at least motivates a suggestion that turning on a temperature then has to somehow change the space-time in the gravitational description in a way that changes its boundary, so its boundary is no longer R4. What we need is some bulk geometry whose boundary matches the R3 cross S1 that we want for a thermal field theory. And of course, it should respect all the symmetries. Introducing a temperature changes the symmetry of the equilibrium state that we're trying to describe, so it's no longer Lorentz invariant, but it is still invariant under translations in 4 dimensions. It's invariant under O3 rotations, so I expect to have a dual geometry that respects exactly the same symmetries. With just that input, there's basically only two possible answers. One answer is basically just ADS5 cross S5 again, but with one dimension compactified. And to give that a name, I'll just call that thermal ADS. In other words, it's periodically and so what is that? All I do is I write down a metric, and you're going to see the same geometry of ADS5 written in terms of metrics in at least 3 or 4 different ways. It's unavoidable, just related by different choices of coordinates. I'm not even going to stick with a consistent choice of coordinates. Sorry about that, because different choices are convenient for different particular problems. Okay, so here is one way of writing a metric for ADS5 where, what do I have here? I have a metric for the S5, and I'm never going to write it in any more detail. You could introduce any sort of coordinates you want to describe a 5-sphere. I have, well, let's start here. I have ordinary 4-dimensional coordinates time t, 3 spatial coordinates x, the little wiggle is denoting a 3 vector, and I have one additional coordinate I'm going to call u, which you should think of as the ADS radius. And I have a factor of L squared out in front, which defines the curvature scale. So I'm going to draw various pictures. Now, in this particular metric, if I just start with this, the u coordinate you should think of as running from 0 to infinity. And actually, I lied. You shouldn't actually think of u as the ADS radius. You should think of it as 1 over the radius. So why is that? Well, you just look here. See, as u goes to 0, this factor blows up. So that's, if you will, saying that the length associated with a certain change dt or dx becomes larger and larger as u goes to 0. In other words, u equals 0 really is the boundary of the space-time. That's the boundary on which you should imagine you have 4-dimensional Minkowski space sitting. All right? As u increases downward, you're going, I'll descriptively describe it as saying deeper in the ADS bulk geometry. Okay, you're going to hear more about this in probably greater detail and with a little more care in other lectures. I'm going to try not to say too much more about this in terms of how you would use this for 0 temperature applications. Unless somebody wants to ask me more about this right now, feel free. I'm just going to look at this and say, what's t here? T here is some coordinate. I forgot to say one thing important. I put a plus sign in front of it. That's because I wrote here a metric for a Riemannian space or a Euclidean signature space-time, and that's relevant for doing equilibrium thermal physics. If you wanted Minkowski signature ADS5, you change it to a minus sign. That's just the same analytic continuation in T. right? But as I just said, I want Euclidean signature. So that time coordinate you should think of as just like the Euclidean time that appears in some Euclidean functional integral. And if you let it run from minus infinity to plus infinity, in fact, as you'll hear more about, you're describing properties of the ground state, vacuum properties of the dual field theory. If I want to do finite temperature physics, the easiest thing to do is to simply say that T is periodic. Nothing in this metric depended on T. So I can introduce an identification and say the point that's labeled by T equals beta, I suddenly regard as the same thing as a point that's labeled by T equals 0. All right, so it's just the same thing as taking an infinite sheet of paper and rolling it up into a cylinder by making a suitable periodic identification. All right, that's what I mean by periodically identified ADS5. And by construction, the boundary of that space would have been R4, except I periodically identified one coordinate. So by construction, its boundary is what I wanted, R3 cross S1. All right, that is a solution of Einstein's equations. Satisfies everything I might want, and is one possible answer for what bulk geometry might be relevant. There is a different possibility, which I'm not going to derive deductively. And I'm barely able to spell correctly, which is, I'll call ADS Schwarzschild cross S5, or an ADS black hole. And it's really kind of sloppy terminology because it's not a metric for a black hole with some spherical horizon. It's really a metric for what more technically could be called a black brane, something where you have a flat horizon that extends forever. Let me just write down the metric. Yeah, that's fine. All right, it's almost what we had up above. All I did is stick in some factor of the denominator in the ADS radius term that I called f of u, and a compensating factor in the numerator of the dt squared term. And f of u is simply some polynomial, well, in particular, 1 minus u divided by something to the 4th power. So what happens? As u increases from 0, this function decreases from 1. Obviously, when u equals whatever this number uh is, the function f vanishes, and it's sitting there in the denominator, so something significant is happening in the geometry, and in fact, well, we'll talk about that in just a second. You should think of u is now running only between 0 and uh. So in terms of making little pictures here, there's now a lower limit in the geometry at some position uh. Okay. Which of these is relevant? there is, I don't know, perhaps a slight sequencing imperfection in these lectures, but it's unavoidable. I'm going to ask you to believe me and ask the other speakers to justify the assertion that what's going to come out of gauge string duality, well, many things are going to come out of it, but one thing that's going to come out is a precise answer to what's the relation between the expectation value of the stress energy tensor, a particular very important operator in the field theory, and what's going on in the bulk geometry. And, well, I'll be more precise about this later, but we'll see that the expectation value of the stress tensor is going to be directly related to information about the asymptotic behavior of the metric as you approach the boundary. A little more precisely, it's going to be related to not the leading behavior in the asymptotic behavior of the metric, because that's going to be boring. Because that you can just read off from what I already wrote there. What's really going to be important is the first subleading term, in particular, corrections to the metric that in my coordinate today behave like u to the fourth. So I'll talk more about that. I'm sure other speakers are going to talk more about that. For the moment, just accept, if you will, that information about the expectation value of T mu nu is encoded in the behavior of the metric. That's all you need to say. Well, and that it's essentially a local relation. As I go to some point on the boundary and say, what is the metric doing as I approach this point on the boundary, that's telling me about the expectation of T mu nu at that point on the boundary. Right? That's all you need to know to look at these two solutions and say, in solution one, you can't tell from looking at the metric that you turned on a temperature at all. Yes, you periodically identified things, but if you just locally study the metric as you approach the boundary, you don't see that. Therefore, in solution one, the only thing that we could possibly get out for the expectation value of the metric will be the same thing we get out for the expectation value of the metric when we haven't periodically identified time. And that's going to be the story about working at zero temperature. That'll be information about the vacuum state.
In fact, it seems that solution one, if you use it, you will always get temperature independence.
Yes.
So it's sort of a prediction for the larger engaged theory, no?
Yes. Now, the one caveat is everything I'm saying is really working in the limit where n is large. And so a little more technically, it's saying that the leading large n behavior is precisely what you said. There can be interesting physics in the subleading terms, but if our goal is to describe a deconfined plasma, this is crazy. We have a field theory with fields that are all in the adjoint representation. There's order nc squared degrees of freedom. You put it in a box, you make it really hot. Surely the energy has to scale like nc squared. And solution one completely fails to describe that. That better be wrong. All right. In contrast, solution two, I have changed the metric, and lo and behold, I have even changed the metric specifically in a way that begins with terms that deviations that go like u to the fourth. So the resulting expectation value of the stress energy tensor is going to differ from what we have at zero temperature by corrections which we will be able to interpret as thermal corrections. And both of these terms can be comparably important. Both of those terms will scale the same way as n becomes large. Okay, so it better be true that solution 2 is the right one and solution 1 is the wrong one. And it is. And I'm not going to prove that. So what determines that? Well, each of these geometries is some solution of Einstein's equation, which is defined by some, if you want, some action principle. We're working in Euclidean space, and you can simply ask which solution has lower action. That should be the one that dominates a functional integral, which is really a functional integral over geometries, which is really hiding inside the complete description here of string theory. There's a little subtlety there in that you have to actually regularize this action to make it well defined. And that's the detail I don't want to go into right now. But it is true that you can do this. You can simply evaluate the action of these two solutions, and lo and behold, you do find that solution 2 has lower action than solution 1. And therefore, in the limit of large lambda, large number of colors, the contribution of physics in geometry 2 is overwhelmingly more important than physics in geometry 1. Okay, let's look at the solution in a little more detail. And, well, right here was a little caricature. What I can't do is draw for you a single picture that captures everything because we only have two-dimensional blackboards and it's a five-dimensional geometry, a usual problem.
UH is related to the temperature, because when you...
Not yet. We're going to do it just one moment.
You mentioned comparing the actions. How you can compare the actions without knowing?
A good point. And so what I'm going to tell you right now is an analysis that should have preceded my assertion right there. So, okay, just to be clear, right, here I made some sketch, if you will, that was trying to capture a bit of what's going on where I essentially focus my attention on the u direction and one of the transverse spatial directions. That's a particular slice of this geometry. Let me make a different picture, which is slicing it where I pay attention to what time, Euclidean time, is doing, and the u coordinate. Right? The only real difference is that Euclidean time is periodic, so I just want to draw my picture differently. Right? There is a circle representing the compactified periodic time direction. Think of that circle as living out at the boundary. As u increases, if you say, what is the circumference of the circle? It changes because of this factor of f of u divided by u squared that's multiplying dt squared. So as you come down in the geometry, what you should think of as the circumference of that circle changes. And by construction, f of u vanishes at UH, where this geometry ends. Right? Therefore, the circumference of the circle vanishes when I get down here to UH. Right? So think of this as something that started as a cylinder, except it's getting smaller and smaller, and it pinches off. All right? One key question is, what's really happening right down there at the bottom? And there's two possibilities. Either it pinches off smoothly, and this is a non-singular regular geometry, or there's a conical singularity there, exactly the same as if you take some sheet of paper, right, and cut a little wedge out and make a cone out of it, and there's actually a curvature singularity at the tip of that cone. That's the same thing as saying you actually failed to satisfy Einstein's equations at the tip of the cone. So to say you really have a legitimate solution of Einstein's equation, there better not be such a singularity. Okay, well, this solution is non-singular and is perfectly smooth, provided there's a simple relation between UH and beta. That they're the same up to a factor of pi. And yeah, let's do that. All right, I could just tell you to go check it, but I think it's instructive. So how do you check it? All you do is you expand the metric about that point and look at it. So let's just check this assertion. So let's look at things when u is just slightly less than UH. So let me write u as UH times 1 minus epsilon squared with epsilon as infinitesimal. All right, so du is then minus 2 epsilon d epsilon times UH. Go ahead and square it. And then come over here and look at f of u. And if u is UH times 1 minus epsilon squared, then go ahead and expand f. And since I took something to the 4th power, you'll see that f behaves like 4 epsilon squared plus higher order corrections. And now you just look at the metric. So I started here with du squared divided by f of u. So that just means take this term, divide by that term. Notice the epsilon squareds as well as the 4s cancel. And I just have some epsilon squared, and UH squared is canceled by the u squared that's over there. And then f of u dt squared. F of u gives me 4 epsilon squared. dt squared isn't doing anything yet, and there's a 1 over u squared, which up to corrections is 1 over UH squared. All right, so as far as just epsilon and t are concerned, that's it. And now all I want to do is look at this term here. If UH is beta over pi, for this particular value here, you'll notice that this is the same thing as epsilon squared times d of two pi tau over beta. So that looks exactly like a metric which is dr squared plus r squared d theta squared. In other words, the conventional polar form of the metric of a flat plane, provided what you're calling a polar angle runs from 0 to 2 pi. Well, my coordinate 2 pi tau over beta, if tau runs from 0 to beta, this is precisely running from 0 to 2 pi. So for this choice of the relation between UH and beta, I don't have a conical singularity. the metric at the tip of the cone looks just like the metric of nice, ordinary two-dimensional space. And for any other value, I would have had a conical singularity. Okay. And this is the point at which I should have said, if you compare the action, indeed you find the action of this solution is lower than that of solution 1. Okay, what do we want to do with it?
The deficit angle go?
Pardon me?
How does the deficit angle go when you are above and below?
In general, I would have a deficit angle which is just proportional to the difference between those two quantities.
The absolute value?
Well, you can have either, a deficit angle can be, you can either have too much circumference or too little circumference, right? It can be in either direction. Okay. So we're talking about thermal physics. The first thing to talk about is thermodynamics. How can we get from this setup answers to questions like what's the free energy, what's the pressure, what's the entropy? The basic ADS CFT prescription is really directly giving you an answer to that by giving you a representation for the partition function. Right? On the one hand, I can represent this partition function as some four-dimensional functional integral over fields, but I can't actually do much with that representation when the theory is strongly coupled. ADS-CFT duality in the limit NC goes to infinity is basically saying that this partition function is the same as what you could get by doing a saddle point approximation to a gravitational functional integral, but that saddle point value is then just the exponential of minus the action of your gravitational theory evaluated on this ADS black hole geometry. All right, so one approach for extracting thermodynamics is to now just go and evaluate this. So what is, well, so the relation here says that beta times the free energy is the gravitational action. Now what is that? Well, there is the Einstein-Hilbert term, which I could write as, some integral square root minus g times the curvature, except we have a cosmological constant. Well, essentially just that. But we're talking about spacetimes with boundary. To actually have a well-defined variational principle, you actually need a boundary term added to the straight Einstein-Hilbert term in the action. That boundary term is commonly referred to as a Gibbons-Hawking boundary term, although as far as I know, it was introduced by York. And, well, we're talking about field theory. You can't completely get away from issues of regularization and renormalization. If you really evaluate this action on this asymptotically ADS geometry, you're going to get infinity. But it's a boring infinity. And so you really need to subtract certain counterterms to regularize the contribution to the action that's really coming from out near the boundary. Okay, we could go through that. But the price is we'd have to carefully talk about what these counter terms are. We'd have to talk about what is called holographic renormalization. And it's a little bit technical. So if I can do it quicker, I'm going to choose to do it quicker. So instead of doing that, I'm going to use another approach, which isn't as logically well-founded, but which I'm just going to tell you agrees with this first approach. And the second approach is to believe Bekenstein and to accept that any time you have a geometry with a horizon, like a black hole or this black brane, that you should interpret its area as telling you something about an entropy. And in this setting, that it really makes sense and it's precise. I'm probably going to regret that. Oh, well. Okay, Bekenstein tells us that the horizon area is related to the entropy by a factor of 4 times Newton's constant. One could set Newton's constant to 1, but I don't actually want to do that. And frankly, I should have included Newton's constant up here. Or I forgot to write it. But to use it, I have to tell you something about what Newton's constant is. And sadly, I'm also going to cheat. No, it's a bad word. I'm going to rely on my colleagues giving other lectures to explain more fully how string theory directly tells you what the relation is between what appears as Newton's constant in this 10-dimensional setting and the underlying parameters of string theory, GS and LS, and via this dictionary then how to relate that to the parameters I'm going to care about, which are parameters of the field theory. So in some sense, in the second approach, this is the non-trivial exercise, and it's simply to get your convention straight about what is the 10-dimensional Newton's constant. All right, and I claim it's that. And if you go through the little dictionary over on the left there, this is the same as a half pi to the 4th all to the 8th over NC squared. All right, the fact that it depends inversely on NC squared is why there's this connection between doing large N field theories and doing classical gravity. Okay, given that.
Excuse me, you slipped in the assumption that the entropy is the action.
Yes, I said I'm just borrowing that from Bekenstein.
That actually is that was Gibbons and Hawking. That's why the Gibbons and Hawking is on that S.
No. Gibbons and Hawking is on that S simply by saying, if you actually vary this action, does it give you Einstein's equations? If you do it cavalierly, you throw away surface terms. And if you're on a geometry with a boundary, that means you're actually being sloppy. So the Gibbons-Hawking term here is literally the integral on the boundary of the trace of the second fundamental form, the trace of the extrinsic curvature. And it's simply a term that for manifolds with boundary leaves you with an action which really has a well-defined variational principle. So that's purely classical. That has nothing to do with discussions of Hawking radiation, this relation between entropy and horizon area. Okay, I did foolishly erase my metric. And I really should have boxed that and left it up here. So that's the 5-dimensional part. Well, all right. And that's the sphere. Okay, so what's the area of the horizon? How do you make sense of that? Well, where is the horizon? The horizon is at u equals UH. That's why I called it UH, U of the horizon. It sits there for all values of x. That is to say, it's a translationally invariant horizon, and for all values of t. The question I want to ask is, what is the area of the horizon right now? In other words, I simply want to pick. I want to forget about t. I want to fix u, and I want to calculate the area of what's left. In other words, integrating over all values of x and integrating over the 5 sphere. Well, I really have a horizon that's infinite in all directions, which is directly related to the fact that I'm really thinking about field theory in an infinite spatial volume. In order to talk about any extensive quantity, I have to, in the back of my mind, introduce some arbitrarily large but finite volume in which to work. So let me imagine that the size of a cube in 3 spatial dimensions is what I'll just call V sub 3. In other words, I imagine that integrating dx1, dx2, dx3 gives me V sub 3. All right, in the metric, I read off that the length for a given change in the coordinate x is scaled by L over u, right? Because this is ds squared. So for each direction, I should multiply this by a factor of L over u. I have 3 such directions from integrating over x. So I'm going to get L over u cubed. From integrating over the 5 sphere, I'm going to get L to the 5th times the volume of a unit 5 sphere. Okay, good. So all I need to know is, what is the volume of a unit 5 sphere? Can anyone tell me? Don't have that in your back pocket? A short exercise, which I'm not going to do for you, but is easy, will show you that the volume of a unit 5 sphere is pi cubed. And u here, I forgot to write, I'm evaluating this at UH, so it's really UH I care about. And once again, UH is fixed to be over pi. Good, put it together. And we will get L to the 8, pi t cubed, my arbitrarily large 3 volume, pi cubed. All right, go ahead and divide by 4 times g Newton, and divide by my 3 volume to get not the total entropy, but the entropy density. Entropy per unit 3 volume. I'll write little s for that. And go ahead and clean it up. The important points is, when I divide by g Newton, and I plug in that value for g Newton, you'll see I get an answer which goes like nc squared. You notice the L to the 8s cancel, as they must. I end up with t to the fourth, as I must, and all I'm otherwise left over with is factors of pi squared over 2. Okay, given the entropy, I can use thermodynamics to relate it to the free energy or the pressure or other quantities. Let's get the free energy just by doing a little bit of thermodynamics. The differential of free energy is minus pressure times change in volume minus entropy times change in temperature.
T cubed or T to the fourth?
It is t cubed because I can't read my own notes. Thank you. So I looked at the wrong line. Okay, so imagine that I start with a fixed volume at 0 temperature, and I slowly turn up the temperature. That's the change I'm doing. The resulting change in free energy is going to have no change in volume by assumption, and then it's going to just be the integral of the entropy with respect to temperature. Good, do it. So the free energy density, that's the free energy divided by my spatial volume, is just minus the integral of the entropy density at temperature T dt. Go ahead and do the integral. Get minus pi squared now over 8 mc squared, and this is where I wanted t to the fourth. And the free energy density is in fact nothing other than the pressure up to a minus sign, as you could think about by in fact integrating in volume at fixed temperature. So here is results for the free energy, and you can go ahead and read some of the references I had up yesterday, in particular that first Witten paper where he really goes through the first approach, and indeed you get the same answer. It works. Yes?
Excuse me, I'm not quite sure I follow how the second point resolves the issue you mentioned in the first, the dysregularization issue, because somehow if you use the SMART formula, which relates the on-shell action to the entropy, you also have a mass term there, right? Which needs regularization as well.
I'm not sure what you mean. What sort of mass term?
So the on-shell action, the Euclidean on-shell action is beta times the mass minus the entropy. So in order to define, so somehow here it seems that somehow you neglected this mass term, which also needs regularization.
I mean, all that, if you just, I admittedly pulled Bekenstein's result out of thin air. I did not derive it.
No, I'm not arguing about that. I mean, you can use this result, I agree. But somehow, like, I'm not sure how you extract the free energy from that.
Oh. The simple way to think about it is to think over here. Stop thinking over there. So if you want to deal with holographic renormalization, you're free to. I'm just saying, logically, think of this as giving us an answer for the entropy density in the field theory. Now forget about the duality. Just use first year basic physics. Thermodynamics in 3 space dimensions. That's all this relied on. Gravity is completely out of the picture. Now, it had better be the case that that's consistent with really doing approach 1, really formulating the question, what is the free energy on the gravitational side of the description? And that does work. It just requires more effort. Okay. I should say that this result famously is 3/4 10 times the result for the free energy density if we were at zero coupling instead of being in the limit of arbitrarily large lambda. And then that same factor of 3/4 relating infinitely strongly coupled thermodynamics to zero coupling thermodynamics will also be there in the pressure, in the entropy density, and so on. Okay, let's do some more. Let's look at some different observables. All right, I talked about Polyakov loops being interesting order parameters yesterday. And you already heard about the appropriate mapping between expectation values of Wilson loops, and the Polyakov loop is just a particular Wilson loop that wraps the thermal circle under gauge string duality. Right? In general, the expectation value of a Wilson loop would have to be something that involves a nasty integral over all world sheets of some string world sheet whose boundary is the prescribed contour of my Wilson loop C. In this large NC strong coupling limit, that integral can be replaced with its saddle point value. And the net result is that this expectation value of a Wilson loop is just e to the minus tension of that string, times the minimal area of a string world sheet, which has, minimal area of a world sheet with boundary C. Except that minimal area now needs to be calculated in the geometry that's relevant, namely our ADS black hole geometry. Okay, so let's look at several applications of this formula. The first one is just the Polyakov loop. Expectation of P. All right, what is this?
Excuse me. I had one small question.
Mm-hmm.
Why the 3/4?
Why? Because it is.
No, I mean, no sort of deeper reason to it than just it is.
Well, what can you say? T to the 4th is dimensions, and that's trivial. And c squared you should expect because we have adjoint representation fields that have nc squared components. And I'm not distinguishing between nc squared and nc squared minus 1, which is what it really should be, because we're in large N. So the only thing that's left over is a pure number. What you do see here that's significant is this is the result which gauge string duality gives you for the lambda goes to infinity limit. If you didn't know anything else, you would have said that this free energy density must be scale like nc squared. It's got to go like t to the 4th times some sort of function of lambda. Without knowing anything else, you could rightfully have said, how do you know this doesn't blow up as lambda goes to infinity? In essence, that's what this whole framework, that's information it's teaching us. That this theory has a free energy density which really does have a finite limit. But once you know that, then this is just some order 1 factor. It turns out to be 3/4. Now, if you say, might you have guessed that or expected that, or how does that compare to QCD? I'd like to come back to that later. Okay, very good. So let's do a Polyakov loop. I already had the most useful picture up here for thinking about what is the world sheet of some string whose boundary is going to be that Polyakov loop. So, right, that Polyakov loop, what do you do? This is really the Polyakov loop at some point in three-dimensional space x, except everything is translation invariant, so the result isn't going to depend on x. So on the R3 cross S1 boundary, at some particular point in the R3, you simply draw a line going around the S1 and you say, that's what I want the boundary of my string world sheet to be. That's precisely the circle that you should imagine is being represented in that picture there. All right, now you want the minimal area of a world sheet that has that boundary. You have essentially, well, you have very little choice. Right? You need a world sheet that has this boundary. It has to live somewhere in this bulk geometry. The only thing it can do is just completely wrap this cigar, if you will, that I've drawn. Imagine that this picture here is showing you what is going on just at one point in three-dimensional space. So there are three transverse directions in which I could deform this world sheet. Any such deformation is only going to increase its area. This is the unique possibility which preserves the rotation invariance of the answer and the three-dimensional translation invariance of the answer. And so all we need to do is calculate the area of that. Good, so let's do it. So all we do is we go back here to our metric. The only part of the metric that's relevant is the part that involves du squared and dt squared, because our world sheet isn't varying in x and isn't doing anything on the S5. So all I really need to do is just look at these first two terms, think of that as a two-dimensional metric, and calculate its area. Good. When I do that, you take the length associated with some change in the u-coordinate, and that has a factor of 1 over f in it, times the length associated with the change in the t-coordinate, and that has a factor of f in it, and clearly the f cancels the 1 over f. So I don't have to go through any non-trivial calculation to end up with a formula for the area which has an integral over t from 0 to beta. It has an integral over u from 0 up to uh. What I do need to pay attention to is the fact that there's this overall L squared over u squared. And therefore, there's an overall factor of L squared there, and there's a u squared down there. OK, do it. Integral over t just gives me a factor of beta. Integral over u gives me infinity. Little problem as we run the integral all the way down to u equals 0. All right, remember, u equals 0 is the boundary. And I guess I should say something that I'm sure is also going to be discussed much more in subsequent lectures. Qualitatively, stuff going on near the boundary you should think of as short distance physics or UV physics. Things happening deeper in the ADS geometry you should think of as IR physics. Notice that that's nicely consistent with our whole story of the geometry here. We got a horizon at UH That's the most infrared part of this geometry, and that's what turning on a temperature does. It changes long-distance physics without changing the short-distance structure of a theory at all. Okay, well, I also didn't carefully discuss regularizing that Polyakov loop. In general, in arbitrary gauge theories, Polyakov loops are multiplicatively renormalized, but in general, you always have to make a short distance subtraction that affects their expectation value by a term that involves the exponential of their perimeter. For the moment, I'm just going to cut off that integral. I'm going to introduce some value of u here that I'll call u sub lambda, because that's supposed to make you think of it's like a lambda that you use as a UV regulator. And it really is playing the role of a UV cutoff. Okay, so once I do that, I can do the integral. And of course, I get that. And my basic statement of gauge string duality tells me the expectation of the Polyakov loop involves the exponential of that. T0 is the string tension, which I didn't write over in my table over on the left-hand side. It's simply another name for square root of the 't Hooft coupling up to a factor of 2 pi. The only thing I really want to focus on in this answer is that it's non-zero. And remember, a non-zero Polyakov loop was a signal that we have a deconfined phase. So we would have been very disturbed if we had not been able to get a non-zero expectation value for the Polyakov loop. Okay, let's do a different application. Let's look at spatial Wilson loops. Well, depending on what contour you pick for a spatial Wilson loop, this could be an ugly problem. So let's make them simple Wilson loops for which we can easily do the calculation by simply choosing a contour that's some circle of radius r. Imagine this is sitting in the x1, x2 plane. Okay, one of the things I want to sort of convey is how relatively straightforward in this setup it is to answer questions that, if you think about it in terms of the field theory, are very hard, but in this gravitational description are easy. So what do we have? I can now, let me try and draw now a three-dimensional picture of my geometry, which is already hard enough on a blackboard. So on the boundary, so this plane is now supposed to be the x1, x2 plane. On the boundary, on that boundary, I've chosen some circle, and that's where I want some string world sheet to end. All right, so I'm going to have some sort of surface which can hang down from that boundary in this ADS geometry and is going to look like some, soap film that you get by drawing a circle through some soapy water and pulling it out. So I now just want to do the variational problem of saying what is the minimal area of some soap film with a circular boundary. And if we were in flat space, the answer would obviously be a flat disk. But we're not in flat space. Okay, well, I'm already going to run out of time. I can't avoid it, so I'll try and be a little bit quicker. So I need to describe a string world sheet. You always need 2 coordinates to describe a string world sheet. You can put coordinates on it however you want. You might as well do it in ways that makes your life as easy as possible. Let me introduce a 2-dimensional angular coordinate theta, which just describes going around. I'm going to have an axis of symmetry. And then let me just use u as my other coordinate on my string world sheet. So my coordinates I'm going to call one sigma, but it's really just a nickname for u and theta. All right, so writing equations which say what I just tried to say in words amounts to the following. U is the same as sigma. x1 and x2 are some, at the moment, unspecified radial function, rho, which will be a function of sigma, times either cosine or sine theta. All right, changing this function is going to change the relation between the radius of the circle and its depth in the geometry. And I want to have boundary conditions that say when sigma, which is u, equals 0, the radius is r. And sigma is going to run to some maximum value, and that better describe the tip of this. And so that's the point where the radius of the circles running around shrinks to 0. Okay, so take this x1, x2, and u, plug them here into the metric. There's no variation in time, forget about it. Out of dx squared, I'm going to get terms which involve d theta squareds. I'm going to get terms that involve rho primes and d sigma squareds. And from du, I'm certainly going to get terms that involve d sigma squareds. If you just quickly do that, clean up the answer a little bit. That's what you get. Let's flip these.
Larry?
Mm-hmm.
Before you delete, your string tension is,
Yes?
it seems to be some double counting here. Your L, the radius.
You're absolutely right. There was some L squared missing there. Thank you. A casualty of spending too much time working in units with L equals 1. Okay, given that metric, to calculate the area, we've got to integrate over theta. We've got to integrate over sigma from our UV cutoff to sigma max times what you get by simply, taking the square root of everything that multiplies d theta squared times everything that multiplies d sigma squared. There's no cross terms, so it's very easy. So out of that, I get one factor of rho. I get a square root of sigma prime squared plus f. And a 1 over sigma squared. And I should have had T0 L squared out in front. And that's whoops, that's not area, that's the actual that's the actual Nambu-Goto string action whose exponential gives me the expectation of the Wilson loop. All right, this is trivial and ends up just giving me a factor of square root lambda. Now I'm supposed to solve the variational problem, varying rho, and figuring out what minimizes this. One can go through that and write it out. It's not something that has a real simple analytic form, but let's just think about the limit of large Wilson loops, enormous Wilson loops, radii arbitrarily large compared to t. And we want to make this area as small as we can. All right, well, what has to happen? Rho here is some function of sigma. At sigma equals 0, it has to be r. At sigma equals some maximum value, it has to be 0. So it has to somehow or other vary from r down to 0. And there's a term that involves the square of its derivative sitting right there in the action. So that's going to increase the area. I want to make that effect as small as I can. Well, what do we know? We know that f here is really a function of sigma. It's the same f that appears everywhere. It only makes the square root bigger. And so f vanishes at the horizon. This square root will be as small as it can be if most of the variation where rho prime is non-zero happens close to the horizon where f is as small as it can be. On top of that, I have a factor here of 1 over sigma squared. Right? That is, well, the smallest that 1 over sigma squared can be is the same thing as the largest that sigma squared can be, and that's the maximum value of sigma. But how large can it be? Well, this world sheet has to fit into the geometry, and the geometry ends at UH. Okay, so imagine some world sheet that looks like a can of soup after you open the top and throw it away. It's the circumference of the soup can plus its bottom. On the circumference, rho isn't changing. So that square root is contributing as little as it can. Rho prime is only non-zero on the bottom of the soup can, where sigma is as small as it can be. All right? If you think about that a little bit, I claim you'll easily understand that in this limit, something very, very close to this world sheet is clearly what minimizes the area. That if you deform it significantly away from this, you're only going to increase the area. And it's a nice answer. Because if we want to understand how this area behaves as I make this Wilson loop bigger and bigger, really all I have to do is think about this part at the bottom of the soup can. That's simply a circular patch on the horizon of this black brain. And it's a patch whose area scales like r squared. So in fact, if you work just slightly harder than I've done here, you can get an actual bound. This action is which way does it go? Greater than, let me just jump to the end, square root lambda pi over 2 t squared r squared. So a simple bound of that integral, in fact, will turn into this result. And that's telling you that in the field theory, the thermal expectation value of the spatial Wilson loop is falling off with increasing radius, like e to the minus some thermal string tension, which is in fact pi over 2 root lambda t squared times the area. In other words, this is area law behavior. That's something I argued had to be the behavior of spatial Wilson loops in asymptotically high temperature QCD when it's weakly coupled. The same argument would apply to n equals 4 super Yang-Mills in the regime where it's weakly coupled. There we could do the same analysis going through the same hierarchy of effective theories and see that spatial Wilson loops satisfy this area law behavior. And here's the same behavior coming out of the gravitational dual in the large lambda regime. Pardon me? This coefficient here is completely different between weak coupling and strong coupling. So in the weak coupling regime, if you go through that sequence of effective theories, the string tension can only depend on the one scale that that last effective theory depended on. That scale was lambda t. So in weak coupling, so this is strong coupling. In weak coupling, this would go like some number times lambda squared t squared.
But again, R and T dependence is purely dimensional count, assuming there is R squared dependence.
Yeah, assuming that the whole description makes sense. So I went through this in part just as part of showing that you actually get out the expected physics, that it makes sense that we are in fact describing this hot thermal plasma. Okay, I'd like to do one more example.
No, we could maybe carry on in the discussion session. That'd be. Is it a while?
Yes, we could do that.
Would that be okay with you?
Sure.
Yeah, let's
Okay.
Okay. Okay, so maybe we can postpone any questions until the discussion session at 5 as well.